Okay, the last video of 9. Again, this should be fairly short like the last one. So we want to talk about what happens when our sigma is unknown. Well, as you can guess, similar to what happens in confidence intervals, we're also going to do the same thing, only now we're going to do a t-test instead of a z-test. So t is x bar minus mu naught over s over the square root of n. And I have my Mr. T test here. This is also sitting in my office. You might have seen it before. It says, I pity the fool that doesn't know their population standard deviation. So this is one really important thing. When sigma is known, we use the z. When sigma is unknown, we use s in place of it, and we use t. So we use a t-test instead of a z-test. So this goes for the same thing for intervals. We use the test and our interval based now on the t distribution, not the z distribution. So not the standard normal, which is the z distribution. This is our test statistic. We're going to find our p-values the same way. So essentially what's going to happen, so let's say that I have, for this first one, I have a left-tailed test, an alternative hypothesis, that looks like this. Let's say that I know that my test statistic is negative 2.6 with n equals 30. So how would I go about finding my p-value for this one? So I'm going to go back to my calculator, and I'm going to say, okay, I want to go to distributions, and you'll have something called TCDF. For some of you, that's number 6. For some of you, that might be number 5. So this has lower and upper already. I don't have to put in the 100. I can just leave the lower at negative 1 times 10 to the 99. Go to my upper, which is negative 2.6. I have to put in a degrees of freedom. So I'm going to put in 29. Because notice I have to put in n minus 1. So if I'm going to write this, if I have a kind of calculator that doesn't come up with a menu like this, I'm going to write this way. TCDF, negative 100. And notice I go a little bit farther out. For standard normal, I went to 10. For the T, I want to go a little farther out. Simply, this is probably overkill, but simply because, of course, the T, has heavier tails. It can go farther out before the probability is so tiny that it's 0. So I want to be on the safe side and go to negative 100. Up to negative 2.6, and I have to put my degrees of freedom here of 29. And let's see, paste, that's what it looks like, equals 0.007. So with this p-value, what would you do? I'm hoping that you guys are thinking to yourself that you would reject the null hypothesis in this case and say, yes, we have enough evidence to say that the mean is less than the hypothesized mean. So let's say that I had a right-tailed test. So I had some kind of greater than situation going. So this is a right-tailed test. And let's say I had a t of 1.7 and n of 25. And yes, if I have a fairly normal distribution, n can only be 25. So I'm going to do this again. Distributions, TCDF. Now I'm going to go from my t, so 1.7, up to something like 100. So I could make it 1,000. I could put as many zeros as I want in here. It doesn't really matter. And now my degrees of freedom this time is 24. And my answer is 0.051. Now at the 5% significance level, would I reject? Okay, no. Even though this is just a D, this is 5.1%. This is do not reject. Darn it all anyway. This is, man, that's so close, and I'm trying to prove something, and I can't quite prove it. That is, get a bigger sample size. If it gets worse, then it probably isn't true. If it gets better, then maybe you can prove something. So finally, we have a two-tailed test. So if I have a two-tailed test in this situation, so this is a two-tailed test. Let's say I get a test statistic of, I don't know, 2.1. Okay. This time my n's pretty small. Let's make it 15. And I want to see if I'm not equal to some number. So what I'm going to do in the two-tailed test, I'm going to do the 1 minus again. Of course, I can also multiply a one-tailed test by 2, but it's easier for me, I think, to just go 1 minus. So I go from the negative to the positive and 14 degrees of freedom. So I'm just going to go ahead and hit 1 minus right now. Then I go to my distributions, then TCDF. I go from negative, whoops, that's not negative, negative 2.1 up to positive 2.1 with 14 degrees of freedom. Paste it. And again, I'm close. So my p-value again, 0.054, do not reject the null. I do not have enough evidence. And you see why I say that. It is almost have enough evidence, but I don't quite have enough evidence at the 5% significance level. And I almost said 10 because at the 10% significance level, I would have enough evidence. So it kind of depends on very much depends on what you're willing to do as far as how much you're willing to be wrong. Okay, so that is how we find the p-value of a t-test if we know this information and we have the test statistics. So again, this is always something you can always find your test statistics by hand and do it this way. However, we can also use our calculator. So how do we perform a one mean t-test using our calculator? Again, a simple random sample. It's either a normal or a larger sample. Now, if we're an extremely large sample, you do realize that the t becomes very close to the z anyway, and it really doesn't make much difference. But like I said, I said this in confidence intervals, but I really prefer that if in doubt, just use a t-test, because as your n gets larger, it'll become exactly the same as a z-test anyway. So you might as well just use the t-test. And sigma is unknown. So this is much more realistic. And these are actually things that statisticians use all the time. So this isn't anything that I'm just teaching you that doesn't get used on a regular basis. So let's say that we have a example. So let's say that we work for quality control for a specific soda brand, Coca-Cola or something like that. I said Coca-Cola. And I want to test to make sure that my soda fills of my 12-ounce cans are not less than 12 ounces. See, so these are less than 12 ounces. If I can prove that my soda cans are less than 12 ounces, or maybe I'm some other kind of consumer group trying to make sure that a certain soda isn't cheating customers, so I want to test to make sure they're not cheating customers, and the average soda can isn't actually less than 12 ounces. So I want to try to prove this. So this is my null and alternative. So I'm trying to prove that the soda people are filling their cans. Oops, spelled that wrong. Less than 12 ounces full when it's marked 12 ounces on the can. So that's what I'm trying to prove. So the question being asked, the thing I'm trying to prove goes in my alternative hypothesis. Now I go out and I get 36 cans of soda. 36 random cans of soda. Of whatever soda this is. Of Coca-Cola. Coca-Cola. See? Not Coca-Cola. Coca-Cola. So 36 random cans of Coca-Cola. And from different places, right? Some are from vending machines. I get them all from different places. So it's a simple random sample. And I find that the average fill is 11.95 ounces with a sample standard deviation of 0.25 ounces. Interesting. Okay, let's use stats on that. So let's do what we need to do here. Oh, yeah, I said 36. All right, so let's do this test. So the first thing we're going to do, so remember, if we did this by hand, this would be x bar minus mu naught over s over the square root of n. So it would look like this. 11.95 minus 12 over 0.25 over the square root of 6. So we would have 0.05 divided by whatever 0.25 over 3 is, or nope, square root of 36. I can't do that. 0.25 over 6. So not sure what that is. Don't think it's very big. You kind of got to be careful with this, though, the way it's done, the way it's written. You got to kind of do that first if you're going to do it. So 0.25 divided by 6 is 0.0 that. And so you have 0.05 divided by this number equals 1.2. Okay, so our test statistic is 1.2. So how do we do this whole thing on the calculator? So what we're going to do is we're going to go to stat, go over to tests. Number 2 is t-test. So again, we're given statistics. Our mu naught is 12 because we want to prove that these are less than 12. We only got 11.95 ounces. And S was 0.25. Oops. I keep losing my dot there. There we go. And in this case, N now is 36. Oops, come on. There we go. And I have a left-tailed test, so I have to click on the left, and I have to click on it to make sure it takes, and then enter for calculate. So again, I look at the top, make sure my alternative hypothesis is what is being shown right here. My t, I lost my negative somewhere in there, is negative 1.2. My p-value is 0.119. So with a p-value of 0.119 at the 5% significance level, do I have enough evidence? So I would say do not reject the null at the 5% significance level. We do not have sufficient evidence to conclude, say PV, to conclude that the cans on average, and I have to have this word average in every time that you guys write a conclusion, I must have some mention of average, are underfilled. Okay. So I don't have enough evidence to say they're underfilled. It's close, not too close. It's 11.9%. So this means that I would get, because I want to remind you guys what p-value means, and I'm going to say this so many times you're going to get tired of listening to me about it, but this means that 11.9% of the time, if you think about your t distribution here, 11.9% of the time, so here's 12, well, actually that's 0, because it's standardized, we're going to get something this far away, okay? So remember, this is 11.95. Well, the standardization, this is actually negative 1.2. So this is our p-value out here. So this is the probability that we get either negative 1.2 or farther away if the null hypothesis were true, because we standardized this using the null hypothesis. Null hypothesis meaning that that mean was 12. So when you look at this, you go, well, this is the probability. So this only had an 11.9% chance of happening, which is fairly small. So you're like, They could be cheating, but the problem is we don't have a big enough sample size. And maybe if we found a bigger sample size, we could find out that the company was cheating. Or maybe they're not cheating and we just happen to get bottles that were filled less than others. So lots of different things and lots of different ways to interpret things. And you can always go and do things again. So we did this. So again, I just have this on here just to make sure that you guys understand. First of all, you see that alternative hypothesis. You always want to check that. Then you get your test statistic. This you need to report. Your p-value needs to be reported. And again, you get all of these things for free. Okay. So, and you compare your p-value with your significance level. Now, sometimes you might be given data, and that's pretty simple to do. I don't even know what I have in here. Let's look. So let's say I don't have anything. So let's say I have a bunch of data that I get, and I go and I look at these cans, and I get like, I'm not going to do a very big sample, but 11.9, 12.1, 12, 12.05, 11.86, 11.98, 11.99, whoops, that was one. I'm only going to do 10. So this is going to be very small sample size. So bear with me, 12.01, 12.1, and 12.03. So let's say that that's what I get, and I want to try to prove that this is less than that. So what I would do, so if I only am given the statistics, what I can do is I can go to test, go to my t-test, and instead of stats now, I go to data. Okay, let me go down here. So if given, data, enter into list. So we're just going to say list 1. Okay, so go to your t-test. Okay, input, switch to data, and then remember to hit enter so that it takes. Then your mu naught, just like before, give it your list, mu naught, list is list 1 in this case. Frequency, in our case, this is going to be 1. And then of course your mu, in our case, this is not equal to, less than, greater than. We want a less than still because we're doing the same thing as before. We hit this. Well, see, our x bar is 12.002. So no way we can prove it if our x bar is bigger than that. But that's okay. So we're still trying to prove mu equals 12. Mu is less than 12. We get an x bar of, and we didn't even know our x bar before, but we don't need it because this just gave it to me, 0.077. So whenever you're given data, I also want you to report these. Okay, so if you're just given data, report these. T is 0.082 and your p-value is 0.53. So definitely do not reject, do not have sufficient evidence to conclude that the bottles, or the cans, that the cans are underfilled. Now this one is one of those silly ones where you're like, well, it's, of course it's not. My average was over 12, so how can I prove that it's underfilled? So that happens sometimes. If you have a lot of data and you run the test, sometimes you don't know that it's going to be, that even if you try to do a left-tailed test, it may become with a really high p-value. However, I want you to be very suspicious of one-tailed tests with p-values greater than 0.5. Be suspicious. I'm not saying never do it. I'm not saying it can't be right, because in this case it is correct. But be suspicious. Check to see if you turned around the less than or greater than sign. Now, if you have a two-tailed test, that can definitely happen. You can get high p-values like 0.8, 0.7, something like that. Be even more suspicious of p-values that are close to 1. So be very suspicious of p-values that are close to 1. You probably did turn it around. If you have something like, if you have a one-tailed test and you do a p-value of like 0.90 or even 0.95 or 0.9 something, you probably turned around your less than or equal or less than or greater than sign. So always check for that. So that's just kind of a thing to see if you were incorrect about that. And so that is it for chapter 9, and we're going to move on to chapter 10 next time.